connecting your world.
Imagine a global enterprise network as a massive, high-speed transit system. A single misconfigured parameter at the data link layer, Layer 2, can trigger a catastrophic collapse of an entire Layer 3 routing topology. These CCNA curriculum standards establish the industry's definitive architectural blueprint, codifying the logic required to build and sustain enterprise infrastructure. We will use this exact framework to construct a functional enterprise network from first principles. Our build will progress from the rigid physical constraints of bare metal Ethernet cabling all the way up to an intelligent, software-defined wide area network. This construction requires stacking disparate, interdependent technologies in a specific, logical order. You cannot achieve high-level routing without a secure, stable data link layer beneath it. Mastering this layered progression allows an engineer to isolate faults precisely, preventing a global infrastructure from failing under the weight of its own complexity. Our foundation begins with the raw hardware constraints detailed in the first chapters of the blueprint, relying on physical cabling to connect endpoints. At this physical level, the network uses Ethernet encapsulation to form localized collision and broadcast domains. Every device plugged into a basic hub or switch hears the broadcast traffic of others. Using a single physical switch for hundreds of users creates a scalability crisis. Unregulated broadcast traffic quickly saturates the available bandwidth, causing a total network stall. To manage this congestion, we utilize Layer 2 switching to logically segment the physical network. By configuring virtual LANs, we fracture a single switch into multiple secure, isolated broadcast domains. Engineering traffic is mathematically separated from accounting. While these zones create order, they establish a hard boundary. Data cannot natively cross between them. Physical segregation is insufficient for scale. Logical boundaries tame the broadcast chaos, but they now require a higher-level protocol to allow these isolated groups to communicate. To bridge the gap between isolated VLANs, we move up to the network layer. We introduce TCP/IP and subnetting to assign a unique hierarchical IP address to every network device. With addressing in place, we introduce the router. This is the hardware designed explicitly to step across logical VLAN boundaries. Using a router-on-a-stick configuration, a single physical trunk line allows the router to handle traffic from multiple VLANs simultaneously, pulling a packet from one zone and routing it into another. With the local building connected, we expand the network scope to external branches through IP routing. Our initial method for this external communication is static routing, where engineers manually program the exact paths data must take. As the network grows to a continental scale, this manual configuration becomes a fatal bottleneck. Human-configured paths are too fragile to survive the scale and volatility of an enterprise. We need a system that does not rely on manual updates to stay online. Transitioning to the ICND2 objectives, the network must shift from manual mapping to autonomous pathfinding. Dynamic routing protocols provide the mathematical solution to the tangled static web. Protocols like EIGRP facilitate rapid internal route discovery using the diffusing update algorithm, or DUAL. DUAL constantly calculates backup routes in the background. If a primary path fails, the network recovers instantaneously without human intervention. OSPF, or Open Shortest Path First, allows us to scale this architecture even further. OSPF organizes the topology into hierarchical areas. This limits link state advertisements to specific zones, drastically reducing the processing load on individual routers. Dynamic routing transforms the network from a fragile, human-dependent map into a self-healing, autonomous organism capable of infinite scale. We now shift focus to the WAN edge, the perimeter where the trusted internal enterprise touches the untrusted public internet. Spanning vast geographic distances requires specialized data encapsulation using WAN protocols like PPP. This geographic transit is cryptographically secured using GRE tunnels over IPsec, shielding internal data as it crosses public infrastructure. At this boundary, Network Address Translation, or NAT, allows the enterprise to conserve the limited pool of public IPv4 addresses. Migrating the entire network to an IPv6 standard provides an architectural alternative that bypasses the limitations of IPv4 exhaustion entirely. To protect the core, we apply Extended Access Control Lists, or ACLs, at this edge checkpoint. These ACLs interrogate and filter incoming traffic layer by layer, dropping malicious packets before they can penetrate the enterprise. The WAN edge is a heavily armored checkpoint, built to protect the autonomous core from external chaos. This vast architecture represents the traditional, hardware-defined state of networking, where logic is bound to physical server towers and routers. The final frontier of the blueprint detaches the network's logic from its physical hardware. This is achieved by separating the control plane, the decision maker, from the data plane, the heavy lifter. Tools like Cisco APIC EM and Northbound APIs allow engineers to software-define the entire network globally, issuing sweeping commands from a centralized controller. We then inject quality of service, or QoS, into this software-defined architecture. QoS actively shapes and prioritizes traffic, pushing highly sensitive voice and video streams ahead of standard data to eliminate latency. To achieve all of this, the CCNA curriculum provides the specific technical logic required to manage the world's information flow. This layered, interdependent architecture provides the ultimate operating logic of the digital world, granting engineers the power to build, scale, and secure the flow of global information.